So a small erratum on the data before the data parallel video start. The PR data parallel was handled by my colleague Haojun Zhao, and in between the making of this video and the main repository, there was like a very small commit of 5 lines, and the main changes was uh, related on the nature of the hook we use on the parameter. So you will discover later the hook mechanism. But just the nature of the hook is it's kind of important, but it doesn't change conceptually the data parallel concept. So we discovered that we rely on a very outdated version of Megatron data parallel, and there's like reason to use a specific hook. And as you can see in this issue from PyTorch, and you have this PyTorch maintainer that explained a bit why we should use a specific hook. But that's it. That won't change the video.
Okay, so hello everyone. Today we are going to talk about data parallel. So just a reminder that in the last video we talked about tensor parallel and how to split our weights. We saw that there was two schema. We can do column wise or row wise. And when we have a stack of multiple MLP layers or linear layers, there was like an efficient schema to combine so that we can save up some communication. And so today it's data parallel. We'll talk about the naive way and then the bucket part. Before So we start to check the new changes in this new step. And so you see there is this new class called data parallel naive. After that, there's a call to distributed sampler, okay. And then here you see that there is this thing. The trend step has been augmented with some new code, okay, with this requires grad sync attributes. So we'll talk about this later. And then we have the API that didn't change much. We call data parallel naive as a class, and then we get the model and we can continue training. It's just before the model apply tensor parallel. So yeah, there's this comment that is important. Need to move the model to the device before wrapping it with data parallel. Because in data parallel, we put a lot of hook, and if we instantiate our data parallel and then move the model to CUDA, because at first it was CPU, then the hooks will not get transferred to the CUDA model, the model on CUDA. And you have this call to model reset. Okay, so before moving on to the core part of the data parallel, I think it's good to have a reminder of how is the training loop structure. Okay, so you remember we start with a number of tokens and we want to reach this maximum number of tokens that we have specified. And once we have done that, we have done that, we see there's a call to trend step that will take into account the model, the data loader at the device to get a loss. Okay, so what is inside this trend step? You see that we loop over the gradient accumulation steps. We fetch some data batch. From that, we we input it to our model to get an output. This output will be used to compute the loss using the cross entropy loss, and then we can call the loss backward. So here you have to understand that this part will compute the gradients. Okay, it's when we call backward, we are going to call the autograd of each layer, and we will compute the gradients. And then there will be a call to optimizer step that will not compute the gradient, but use this computed gradient before and use it as to update the parameter of the model. Um, Using the optimizer rule update. For example, it's in our case it's Adam, so it will use the Adam algorithm to update the weights using the gradient. So there's these two distinct steps. First, you compute layer by layer the gradient, and second, at optimizer step, where you actually update the weight using the gradient. Okay. So let's go back a bit to the whiteboard. So there is this thing we will talk. We will not focus too much on it, but it's still good to know. So remember that data parallel is applied on the batch size dimension. What I mean by that is it's going to consume more data from your data loader. So you're going to fetch data, send it to each replicas, but the data will not be the same. So you have your data set, okay? I'll draw a small box like this, data set. Let's say it has 4 data. I'll just annotate with some color: orange, green, blue here, and orange here. Okay. So you have to find a way to distribute data to each replicas, but not the same. So for example, this one will go here, then the green one will go down. Why not? Huh? And then have a blue one that goes down. Okay. And then we have the orange one that is going to go up. Okay. So how do we actually decide from the dataset where to send to which replica? Well, that's the goal of the distributed sampler. Okay. I think dataset deserve a whole video by itself. So it's okay. We plan after this tutorial. There will be a lot of videos like context parallel, FSDP, such things like that. But for now, we'll just assume that the goal of this distributed sampler is to take samples from the dataset and send it to the proper replica. So we'll take a look at the code to see how we do that actually. So there is this call to distributed sampler. So we rely on the PyTorch API. You put the tokenized dataset, you put your number of replicas and the current rank, and you are going then to input it here because we are using the data loader here. So we have to put the sampler so that it knows that we use it. Okay. So now that we are able to send data to each replicas, we can start to understand the high-level overview of what data parallel is doing. Okay, so I'm going to copy paste this. Mhm. Okay, so we have this like this. Okay, okay. So what you have to understand is since you are seeing different batches of data in each of replicas, you compute the forward and the backward. So wait, I'm just reducing this. So you compute the forward and the backward here, plus backward. So your replicas will have different state since they have seen different batches. Okay? And so remember that at some point, we are going to, after successive number of forward backward, we have to call, so this is the step one. At the very next step, we have to call, we have to, well, before moving to the next step, we have to call the optimizer step. If you remember the small recap we did with the training loop. Okay? So we have to do this whole thing again with new data and stuff. Just put it here, okay? So we have to call optimize step that will take the gradient that we have computed here, okay? And use it to update the parameter. But since the replicas have different state, it means that we are going to optimize, we are going to update each replicas with the gradients that are different from in each replicas. So at the end, when we move on to the step 2, we have 2 replicas with different state, which is not correct. So that's why we have to find a way to synchronize the state, okay, before doing the optimizer step. If it doesn't make sense to you to why we have to synchronize the state, well, we actually call them replicas, which means that they have to be the same, right? Since they are replicas. So here we have to synchronize
sync the state, and then here, it's in gray, up, same state. What I mean by same state is actually same gradient. So we sync the state at this point, and once we sync the state, we actually have the same state here, and then we can call optimizer step to update the parameter of each replicas because we have the same gradient in each replica, and thus after optimizer step, we have the same updated parameter in each replicas. Okay, so what can we talk about this? So, okay, so what I mean by sync state is actually syncing the gradient. Because we are seeing different batches, we do different forward and backward, so the gradient will be different. So how do we do that? We actually call a null reduce operation, which will do an average, basically, of the gradient. An average of the gradient. I think we have to make a picture, a better picture. So we go down in an abstraction to understand how do we sync the gradient. And after that, I will tell you in terms of, I will draw a small drawing that explains how everything fits together, and then we will check on the Perfecto profiler to see if it's correct or not. So what I mean actually by averaging the gradient is, okay, assuming that here you are computing the forward, okay, so forward go this way and backward go this way, okay. Okay, it's not this color here, okay, just, okay, so it's the new things that I will draw. So you do one forward EC, one forward EC, here, 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 okay? Same go for the second replica. And then, once you have done all the forward for all the network, you do the backward, okay? You start to do the backward. Okay, I will draw one by one. And every time you draw backward, what you have to do is sync the gradient of this specific layer, okay? And then you do the next backward, and sync the gradient. You do the next backward, again, sync the gradient, backward, backward, so we are the decoder, we sync the gradient, backward, backward, we sync the gradient, and backward, backward, and we sync the gradient. Okay, so that's how actually the all reduce, the data parallel naive is acting. So it means that we start with some forward, okay? Let's say we have 3 forwards, another forward, another forward, okay? And then after that, you call the backward as we have drawn before. And once you call the backward, you call the all reduce to sync the gradient, okay? And then you repeat this operation until you have no more the same amount of forward and backward. Up. I would reduce the size a bit, like this, and then you go like this, okay? And once you have done that, you have the whole gradient that is synced at this spot, because it's the last all reduce, and then you can call optimizer step, because you now have the same gradient in each replicas, and you can use this gradient in each replicas to update the parameters. Okay, makes sense. So let's verify this in the profiler. So I have profiled I have profiled a bit the data parallel naive, and you see here that we have a forward, backward, and then we have forward, backward, forward, backwards. And just take a look at what happens in the backward. I put all reduce here, so it will find every mention of the all reduce. Sorry, up.
And you see there is like yellow thing here, so it means it's the presence of the all radius. So let's take a look at yeah. So you see here there's like this MNL loss backward, so it's basically when we call the loss dot backward, and then you do logs of max, blah blah blah, and then you do some computation. So it's the backward call in here. So it's the first backward. Let's say it's the first backward. And at some point, you see that we are going to call the all radius. Let's find it. Okay, there's the all radius here, okay? You see? So we did a bunch of computation, and in the same so this whole thing here is called a stream. In the same stream, we are going to call the all radius. Then we move on to the next layer. We call the backward, and after that, we are going to call another all radius that is here. Okay, I'm not sure if you're seeing this, but it's always backward and then all radius, backward, all radius. Okay. So now that we have proven that our drawing is correct through the optimizer, through the profiler, we can take a look a bit on the implementation details. So I didn't specify it, but we trigger this sync only on the last batch. Okay. So when we are on the last batch, we are going to trigger this mechanism of calling the all radius after every computation of the autograd. Because there's no point to do it at every step, because what we want is after the last batch, we are going to call optimal step. And it is only at this point that we want to make sure that our states are the same in each replica. And then how does it work is we are going to attach a hook. So a hook is a function that will be triggered when another function is called. For example, here the backward is called as the backward, and after every call to backward, there will be this function all radius grad that will be called after that. So this hook, this function register backward hook will go over every parameters, and and for each parameter it will register a hook, and the hook in question is the all radius grad here. And what it is doing, the all radius grad, it is going to run an all radius sum and then divide by the DP warp size. So basically, it's going to average the gradients across replicas. Okay, so we have now taken a look on the data parallel. We can, I think, move on to the next step, data parallel bucket. Okay, so let's see the new changes in the step 6. So you see that there's a new file called bucket. Okay, bucket manager, data parallel bucket, sure. Then you have this function train with the new just a call to data parallel bucket, and that's it. So I think we can go back to the whiteboard to understand why do we need bucket, okay? So if we take this drawing back, I think it's very important. We can see that this drawing is very naive in a way. Because if you remember, at the every backward, I was drawing one backward at a time and then triggering one sync of the gradient at the time, okay? What we can actually do is to group them somehow, since there's no obligation to run only one backward every time. We can do, for example, two backward, two backward, and then start to do a syncing of the gradient. Then going on with the two backward, sync of gradient, two backward, sync of the gradient. Okay? So the reason we do that is actually to maximize the bandwidth of the all radius, the bus bandwidth. Because doing one by one is not very efficient in terms of bandwidth. So we can actually group them or bucket them, if it's a better word, group or bucket parameters to maximize bandwidth of all radius. So that's the first optimization. Second optimization, if I take the drawing back,
that we can do is wait, okay, is so the second optimization is, if we remember, the during the training step, what we actually do is only computing the autograd. So this whole thing here is just the order reduce, okay? I mean, no, sorry, the trend step where we compute the gradient. So the only thing we care about syncing the gradient is at before running the optimizer step, the gradients are the same in each replicas, right? So what we can do is we can actually sync the gradient while computing another autograd. There is no reason that we have to first compute the autograd, sync the gradient, wait for it to finish, and then start the computation of the next gradient of the next layer. It makes no sense. What we can actually do is, so we start with computing this gradient here, and then once it's done, we can run all reduce but asynchronously. And while it's running, we can directly start to do the computation of the next layer and continuing to run the next all reduce asynchronously and continue computing the gradient of the next layer and so on and so on. So, so as long as we finish everything, as long as before running the optimizer step, we make sure that all the all reduce has been finished, then it's fine. So the second optimization is just to be overlapping, overlap the compute and the communication. Compute here is being the autograd or the computation of the backward, and here it should be the all reduce. Okay, nice. So we have now understand conceptually the both of the optimization. I think it's good to take a look at the profiler.
So you see, it's the same thing here. We have forward, forward, backward, forward, forward, backward. And then we have this yellow thing that represents the call to all reduce. And you see here that we start by doing the loss backward, loss of max, da da da. And then we reach this point with the hook where we call all reduce. And you see that while we compute the next layer backward, layer norm, there is this call of all reduce that is at the same time computing, but on another stream. So we have two streams here, not like in DP naive, where we only have like everything happening in the same stream. Here we have a stream of compute and a stream of communication happening at the same time. Okay, so what we have seen in theory applies apparently in practice through this profiler, and now I think it's time to take a look at the code.
So we start with this class called data parallel bucket. So you see we are going to initialize a bucket manager. We have this bucket cap megabyte. So basically, I just make a drawing. You can think of the bucket as as an array, big array that we delimited by I don't know, like let's say 3. Let's say go from 0 to n, and then here the 10n. Okay, why not? This thing here will be the bucket 1. This thing here will be bucket 2. And bucket 10. Okay. And so the idea here is that the megabyte here is the number of bytes your layer will take, and it will be the size of a bucket basically. And this 1024 squared is basically just translating megabyte to byte. Okay. So now that we know about the bucket manager, let's see how do we actually fill this bucket. So we call initialize bucket because in bucket manager there is at the very end initialize bucket function. So we are inside the initialize bucket function, but here we are not going to actually create the bucket and fill the bucket. We are just going to create a mapping from the parameters to the bucket location. So if the bucket is empty, what we are going to do is call this part. So if the bucket size is equal 0, then we can just do a mapping between the number of parameters, I mean, our parameters to the location, and we, at this point, we put some information like the start at 0 to every number of, all the number of elements in the parameter, and the current box ID it's going to belong to. And once once you want to keep adding the parameters, you do the same basically until it reaches a point where it's full. So here it's full. And what do we do? Actually, when it's full, we just move on to the next bucket. We increment the current bucket IDs and we just move on to the next one. So what happened is like, let's say we have like the layer 0 Qproj, okay? So it's here. It's here. So I first add the Qproj. It's on the first bucket, of course. So I note the 0 and the number of element here. So it's basic. So I note the 0 element here and the number of parameters it has. So it will be the size of this layer. Then I move on to storing the layer 0 Kproj. Okay. And it's here, and it actually fills the current bucket. So when we want to store the layer 0 vproj, we move on to a next bucket. And that's what we currently do in this code that I have shown you. And after that, we move on to this part. So this part is going to just gather some information about the bucket size and the parameter in each bucket. Just another way I mean, we need actually to gather some information that we will use just in a few minutes. And in the next step is we are going to actually create the bucket, okay? So we initialize the gradient list. We have their size. We know where they are located, okay? Thanks to previous step, and now we actually create the bucket for to hold the parameter. So we have a list of buckets basically, and let's check the bucket class. So I think I have highlighted somewhere. No, okay, yes. So we have a bunch of attributes like the parameters, params with grad ready, which is a set, blah blah blah. And then we have a call to reset some of the attributes. So now we have created a bucket. We can go back to bucket manager. Yes, so once we have a list of buckets with some gradients, okay, at least we know the size, we didn't fill it. Now we have to fill I mean, no, we're not filling yet. I think we are going to actually, yes, we are going to retrieve the grad data and populate it in a new attribute of the parameter. And we are going to see in a few steps why this is important. Why don't we fill, for example, param.grad? Why do we actually just don't use the default param.grad, and why do we have to go with this temporary variable main grad? We could have called it like, I don't know, ABCD, but we gone with main grad because there's more meaning to it. But we'll see in the next step why it's very important. Okay, so now that we are done with data para bucket, so far we were looking at the bucket manager, and after the bucket manager, there is a call to register backward hook. Okay, so here is the register backward hook. So there's something happening which is weird here, is that we iterate over every parameters, and if there is a gradient, what we are going to do is to fetch the accumulate grad object. So this line here is going to fetch the accumulate grad object, like in the autograd graph. You have some node every time you do an operation, and actually when you do gradient accumulation, there is like a node. So what we do is we fetch the next function. I mean, we actually get the gradient accumulator function, and we on this gradient accumulation node, basically, we are going to attach a hook called makeParamHook. So this is linked with the main grad, and we are going to talk about this in a few minutes because it's very important. So two things to remember: we somehow populate the main grad with some gradient, and second, we are attaching a hook to a grad accumulated node. It's weird, but it's very important. Okay, so now I think I owe you some explanation. So you see here in this hook that we attach at the grad accumulated node, we are going to actually accumulate the gradient. So we are currently doing gradient accumulation manually and actually accumulating in the main grad attribute that we have created. And we set grad to none, the default grad of PyTorch to none. But why is that? So basically, there's this issue that explains that when you do gradient accumulation in Megatron, usually your model is in bfloat 16 and you want to accumulate the gradient, but the gradient accumulation is done in float 32 to have more precision. But the thing is, in PyTorch, the native gradient accumulation expects that the weights and the gradients are the same type. Okay? So that's why here, since we want to accumulate in float 32 and our model is bfloat 16, we cannot rely on the PyTorch native API. So we have to find a way to accumulate the gradient by ourselves. So the first thing to do is to create a temp variable that will be in float 32, so main grad. And second is to actually do the computation of accumulating the gradient. And how do we do that? We have to attach a hook at a very specific node, which is the grad accumulator node. Okay, so that's the reason we do it this way. So then after that we have this whole block. So let's see. Yes, so this part is only triggered when we are at the last batch. And what we actually do is we are going to attach. Not attach, but yeah, calling a callback after the call of the backward pass. Okay, so every time your parameter will call backward, there will be this post backward function that will be called. And let's see. We'll see later what it does, but see that after all of this, you have this mark param as ready. So mark param as ready is basically making sure that your bucket is full. So this is bucket manager. Okay, this is its function of mark param as ready. It's calling a bucket in question and calling mark param as ready as well. So we can go back to mark param as ready. Okay, and mark param as ready is adding the parameter in the bucket. So in the attribute param with grad ready. And once this param with grad ready is full, so equal to length self param, then we can call the sync gradient. And what is the sync gradient doing? It's going to actually launch an average, all reduce average. So you see grad data divided, all reduce, but in the async way. So you are going to call the async, and this async will spawn a new stream that we have seen in the profiler, the second one, and so that the communication is not happening at the same level as at the same level as the computation, and it's not blocking. And we have to take it in the self handle. It is very important because once you do async, you have to make sure that it's finished at some point. Okay. That's why you have this wait function that we call self-handle wait. So let's go back a bit on this part. So you've seen that, okay? What this thing is doing is accumulating the gradient. And if we are at the last batch, it's going to call backward. And if backward is done, we are going to call this post backward function. And once everything is done, we have to make sure the param is ready. And if it's ready, the bucket is full, basically, we are going to call all reduce. But what is this post backward doing actually? So let's take a look at this part. So you see that what it is doing is we are going to copy the main grad to the grad attribute, the real one from PyTorch. So why do we do that? It's because optimizer step will need the gradient to update the parameter, but it doesn't know about the new variable main grad that we have created on the fly. So it only knows pgrad. So that's why we have to make sure that all the gradients
is copied in the default PyTorch attribute grad, so that when we call optimizer step, it can use this gradient to optimize to update the parameters. And you see here there's a call to bucket manager weight. So basically, we have to make sure that the very last all reduce, okay? So the very last all reduce, I didn't do the schema to represent the call. So I can take this. I think it's the same. Yes, I can do it. I don't know, I can do it here, okay? So actually here we are no more doing this kind of thing. We're just going to all reduce here like this, or reduce here like this, or reduce like this, because it's happening at the same time, and we are overlapping. So this is data parallel bucket here, okay? This one is data parallel bucket. DP bucket. And so here, before doing the optimizer step, what we want is to make sure with this handle weight, bucket manager weight here, before copying the gradient, that this all reduce is finished, and then we can copy the main grad to grad, and then we can call the optimizer step. Okay. So we check a bit the bucket weight, and in the bucket weight, sorry, it's called handle weight. So it's basically taking, this all reduce when you do async, you have to retrieve you have to retrieve the handle so that you can wait later. Okay, so it's good. And now once you have finished the trend step and optimizer step, and you want to move on to the next step, you have to make sure to call the reset function. So basically, it's going to, we have seen before, to bucket manager. Here, call reset, and each bucket will call reset, and the reset function is going to be this thing here where it sets basically some attribute to 0. We restart the whole process that we have described so far again. Okay, so I think we have now understand what is data parallel naive and what is data parallel bucket. So I think it's good to do a recap between what is different between data parallel bucket and what data parallel naive. So I think naive here, it's going to, for example, in terms of gradient accumulation, we are going to rely on PyTorch default grad hack, okay? But here we are going to manually do grad hack with in a temp variable that we have created. So that's the difference. So actually it means with the data parallel naive that you cannot, it's technically not correct. If you want to train your model with the data parallel naive and the model is in bfloat 16, then your model is not correct. Your training will not be correct because you will be training in bfloat 16, but the gradient will be still in bfloat 16 in terms of accumulation, and it can create some problems. But it works, the DP naive works if you train with in float 32, your model is float 32 and your gradient is float 32. Next thing that is different is not only the gradient accumulation, is the way we sync the gradient. So in that DP naive, we launch an reduce per parameter, and we this all reduce is blocking. It prevents the next computation of the gradient. But in DP bucket, we actually run all reduce on some on buckets of parameter, bucket grouped of params, and this one is not blocking, it's async, so that we can go on to the next computation of autograd and continuing doing the all reduce of the previous layer, and it's done on different stream, so asynchronously. Okay, so it's good. So we know the differences. I think now it's the time to run some training. Okay, let's take a look at the train. Okay, so the train here. So you remember here, last time in tensor parallel, it was 1 here, 4 here, 8 here. So we can do 4 times 8 with 32 global batch size. And then the total global batch size with token was like this, okay? 496. But here, since we have 4 replicas, it's going to be, I want it to match the same global batch size, so 4 times 8, and I have to set the micro batch size to 1. And the global batch size with token is the same. So yeah, when you actually, what's happened? Torchon command not found. What does it mean? Deactivate. Why is it Torchon not found? What happened to my env? Okay, I just need to reload my terminal. So when you use data parallel, you have to be careful because it's going to increase your number of data. So that's why we actually call this data parallel works on the batch size dimension. It's because it's going to increase your number of data you will be feeding. So you have to balance this micro batch size and DB size. You have to remember here we have in total 4 micro batch size, despite putting in 1 here, but it's because we have 4 replicas. So now we are going to run a small training just to see if it works and if it matches with the other runs. So we run only on 8 steps. It's not a lot, but if we look at the Picotron tutorial, we see that the loss here is matching at the very first step, and 8 step is a bit noisy, but it's okay because after a lot of steps it's pretty much the same. But here we just want to check the training if it works. So you see we have the same number of tokens in total. We are filling the correct number of tokens. We train for 10 steps. We'll refresh. It will be a bit noisy, but it will be somewhat similar. And you see, where's the data parallel bucket? It's not displaying. Why is not displaying? It's here, no? Ah, yes, it's displaying. Okay. So you see the loss is quite the same. It's just like a bit noisy because it's at the very beginning. But yeah, it will be after a lot of iteration the same. All right. So thank you for listening. This was the third video before talking about pipeline parallel, and thank you very much. Bye. Hop là.